Okay, so like the title says, let's make a distortion. We started on the app already. Let me get it pulled up. What do we have so far? I started making a channel strip. I think we've got a combo box with some oversampling stages in it. I implemented the oversampling logic, and I also showed you how to manage audio parameters with tree state with new updated method to actually use them. Okay, cool. Here's our app. Awesome. Looks amazing. So if we're going to start with DSP and do some distortion, let's go to the plugin processor and go all the way down to this section that says create editor. We don't really need our actual editor. We can do generic one, which will give us sliders and buttons for the parameters that we put in the layout. So I can do new juice generic audio processor editor. And the only parameter we have right now, the oversampling choice. So now when I hit play, it will go back to the ugly juice green background. And there will be one like combo box that is auto generated. Perfect. So now we don't have to fool with the GUI until we are actually ready to. Okay, so let's just dive in. We already have a folder called DSP. We have our process block in there. So what should we do to keep this all organized? This is where all the DSP calls are going to be, where we process each one. So if we go into DSP and we do new directory and we say, let's do modules, I guess. And in modules, we're going to create a header. So let's just call this, let's say console. So we can get rid of this stuff and just use prog once. We don't need that header guard stuff. To get rid of this little warning right here, we need to go into the process block, which is where we're eventually going to call it. And we just need to put the include so that it sees it. And that's going to be in modules. There we go. Okay. So what do we need for this module? Basically, we need a prepare and a process method, at least. Let's wrap everything in a namespace to keep it nice and organized. Call it Viator DSP. Let's see. Yep, and then we'll make a class and we'll call it console. What I already forgot what I called it. Oh yeah, module. Console module. And for now, that's not gonna inherit from anything. We'll just do a basic class like this. Console module. I don't know if we're actually gonna need to do something with the constructor, so let's just do that. And then I don't think I really ever need a destructor for a DSP class. Give it a private section. Okay, cool. Let's do a prepare method. I'm gonna kind of shy away from what I've been doing recently and go back to using just the juice process spec because I think it's just easier. And there's really no reason not to unless we get to that point and it causes a problem. We'll have to address it. So let's just call prepare. And this will take in a reference to let's see, I need juice DSP. And then we can do juice DSP process spec. We'll call it spec. Okay, not sure what we're doing with that yet, but let's move on to process block, which is going to take in a block. And I guess we'll also take in the number of samples. So let's do juice, DSP, audio block. Yep. Say float for now. Reference block. And then we'll do a constant num samples. Very good. Very good. Let's kind of set it up with templates because that'll follow the juice DSP modules style, and it'll allow us to do some SIMD optimization later whenever we're ready for it. So let's just go in and do that. Let's see. Let's just go to the juice modules and look at like the compressor or something. We got juice, DSP. The simple ones are in widgets. So we can even just look at gain. Yep. We just give it template type name. Float type seems like a bad name. Probably give it like sample type. Yes, 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 yes. This is interesting. I need to look up what this means. This might also be able to help us. Juice vector call type. I'm sure that does some kind of optimization. All right. And then we just do, yep. Okay, cool. So all we really need is this template. And then anytime we want to use the template type, we pass in whatever name we give it, which for us is going to be, I think I'm going to do sample type. And then that should mean that when we go to instantiate this, it will ask us for that type. So we do, no, not juice, Viator DSP console module, and we'll pass it float. And then we'll say M console module. Let's make sure that builds. And our plugin built, so we are good. Looks like that template type name stuff worked. Let's actually do some stuff. I actually found something good. I did a lot of research in chaotic equations when I was in grad school. And if I go to Desmos here, I'll show you. And also if I do list of chaotic maps, this one right here. I took one of these and I just found one that's a simple discrete one, like this one, the circle map. And I just took its equation and since it's one dimensional, I just plug in anywhere it says O of I, I'll just plug in our input there. And yeah, it's pretty simple. I'll show you on Desmos. So the equation is, xn plus omega plus k divided by 2 pi times sine of 2 pi x. And this is what we get. I already saved it over here. Where is it at? Circle map distortion. Okay, here we go. X plus k divided by 2 pi times sine 2 pi x. And you can see when k is 0, our signal is perfect. It's not distorted in any way. It's a perfect sine wave. And as we raise this, it gets distorted. And this was a cool find. It also sounds a little compressed. So you can see where it flattens out right here and then goes back up. That gives it like a kind of compressed sound. And if you go negative, it does a different shape, which looks interesting, but it actually doesn't sound great. And I tried it out a lot on some like drum material and some kind of melodic material. And I just couldn't get it to, you know, sound good for whatever reason. So I'm just sticking with this because it actually sounds good and distorted and warm and a little compressed. So it kind of models tape a little bit. So yeah, here's the equation. We're just going to plug that in. The only annoying part is I talked about a minute ago that we might want to try to implement the SIMD optimization stuff. And with a sine function, we can't really do that. So if I do end up figuring it out, or if I do end up wanting to do that, we'll have to figure out how to SIMDify the sine or accomplish this without a sine function. But it doesn't matter. It's not like this is really high CPU usage anyway. So let's just implement it. But before we just plug in the equation, we need one thing. Let's grab 2 pi and put that into a variable because we don't need to calculate that every sample. We know what 2 pi is. So let's go here and we'll say static const expr float. And we're going to say 2 pi equal to juice. Let's see, math constants float. And you go into it and there's a pi. So, and then almost forgot, multiply by 2. Okay, cool. There we got 2 pi. Great. So let's do this. Return input. Already forgot. Plus. Oh yeah, we need like a drive, like a K. Okay. So let's do that. Let's do let's do a smooth value. So we'll do this. I think we only need one. So this will, instead of input, I'm going to call this drive. Cool. And then we can just do this. For auto drive in, drive smoothers, drive dot reset, spec dot sample rate, and let's just give it 20 milliseconds. We don't really need to make a, yeah, let's not even make a separate function. This is small enough that we can just do it in the process block. There's really no reason to break it out. So let me grab a block loop, and we're going to plug it in right here. Xn is equal, or I'm sorry, Yn, which is usually output. Like if you're looking at any kind of scientific paper or math paper or engineering paper, usually input is Xn and output is Yn. So yeah, so we already got Xn. So Xn plus, and then let's get our drive. So let's make a variable up here. Float drive, or we could just call it K like it is in the equation. And we're going to say M drive smoothers. And we have 2 for 2 channels. So let's use channel as the index, and then get next value. That's what gives you the current smooth value. And I'll show you how to set it in a second. So this is going to be K divided by 2 pi times STD sine, and that's Xn times 2 pi, right? That's it. All right. So let's just make a setter real quick. So we're going to do void set drive. We'll take in a const float. And all we need to do is loop through the smoothers and call set target value. And that's in decibels. So we're going to need to do this. Juice decibels, decibels to gain, and then value. Pretty easy. Cool. So when you call set target value, it will tell it to start ramping up to that target. And that will be it. So now we just need to actually put this in our process block. So let's go here. So we're going to say m console module dot prepare, and we'll pass it this spec that is already upsampled, because in our processor we have 5 versions of this process block. One for no oversampling, one for 2 times, 4 times, 8 times, and 16 times. So whenever you write something in here, that the switching is taken care of outside of it, so you don't need to worry about it. And this repo is on my GitHub, by the way, so you can all download it, and I will push changes at the end of the stream. So prepare, then we call process with this upsampled block, and that will upsample if we're on the upsampled one. Oh, and we also need to pass it num samples. Now, did I actually use num samples? Let's see. Yes, I did. Okay. Now you're going to want to pass num samples to your DSP modules, because some DAWs, especially FL, does this weird thing where it could randomly just give you a like 2 sample block for no reason. And if you're always relying on basically like an alias block that isn't in our main process block, like in the plugin processor, you're going to get weird clicks and distortion and stuff. So I've been just doing this as a no matter what. And we need to call set drive, and that will be it. So where do we do that? In process block? And we don't have a parameter for it yet, so let's go up here, and I will just copy the names into here. Cool. All right. So we make another parameter, and this is the cool new way, not new way, but best practice way to use parameters now, because using the get raw string lookup apparently can be really slow. So if you just set a pointer pointing to the parameter at the start and you just use that pointer, it's much faster. I mean, it is a little annoying having to do things in two spots because we still have to go into the processor and put it in the layout, but it's fine. So, okay. So now process block. Yes, we need a update method. Update parameters. And this needs to take in our parameter thing right here. Where's it at? This, which I already forgot the type. Oh, the type is right here. Yes. Okay. So we need to take a reference to that, I think. Call it parameters. Is that fine? Yeah. Okay. And then we would do this console module, set drive parameters. Here's the cool part about the pointer. We'll do dot console drive, and we just do the pointer dot, and we do get, and that gives us our float value, and without using a string lookup. But remember, this is 0 to 10, so we need to multiply it by 0.1, and that should give us 0 to 1. Cool. Oh, because it's not decibels. I forgot. This isn't a normal drive. This is going to be 0 to 1. So I guess we just need to pass in value. Yep, that's what it is. We need to call parameter change. Okay, so I think we could just take the same pattern, right? And oversampling choice, blah 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 blah. Instead of calling process, we're gonna call what is it? Update parameter. And then this is gonna be m parameters. But we gotta dereference it, right? Because it's a smart pointer. Yeah, okay. All right, so let's just run it one more time to make sure that little debug thing is printing out the numbers we expect. 0, 1. Perfect. All right, so we can take this out. Build. There we go. It's going to work this time. I feel it in my bones. Yep, look at that. All right. Cool. Okay, here's logic. Let me hit the loop. Where are we at? Channel strip. Here we go. Distortion. Okay, should be able to hear it being a little compressed all the way up. And then just a little warm and driven as we go back down. So this could be good for a tape model because you got that natural compression. So that's pretty simple. We can add some more features to it later, but that's our basic wave shaping and distortion. So there you go. All right, that's it for this one. Thanks for watching. See you next time.